This is Module 12, Lesson 1. In this module, we're going to start looking at the states of matter. And we're going to look at how the particles are arranged differently in those different states of matter. And we're going to spend actually most of our time talking about gases. We start there, and then we're going to do some math with gas problems. In this particular module, about half of it is concept-based and about half of it is mathematical. So the concept-based means that you have a lot more vocabulary to learn. You have facts that you can memorize. Some of you will find that to be refreshing. Some of you will wish that the math would come back. The math will come back towards the end of the module, and in that part of it, we will be doing some formulas where you plug in numbers and you have a definite pattern to what you're going to be doing. So hopefully there'll be a little bit of something here that you like, no matter what your preference is. During the concept-based part of this stuff, the videos are going to be shorter. And I'm not going to read everything to you that's on the screen. You can pause the video and get the information off of the screen while it's paused. That way you're not listening to me just read it all out to you. So the first thing that we're going to do is look at the meaning of the word kinetic. We have two kinetic words here. We have kinetic energy and kinetic theory. Anywhere that you see kinetic, it always means motion. So we're going to be looking at the kinetic theory of solids and liquids and gases. So it's important to understand what the kinetic means in that. So you can get the rest of this down and move on to the next slide when you're ready by pushing play and resuming the video. All right, now specifically for gases, the rest of this lesson is going to be entirely about gases. Here are some things that you need to understand about gases. Like, you need to memorize these things about gases. And keep in mind that on test, I may put this in slightly different wording, so you need to understand what these things mean. So if we draw something like a beaker or a cup right here, and inside of this container, let's put a lid on it too. So we'll put a lid over the top of it, and we have some gas particles floating around inside here. Gas particles are assumed to be tiny solid spheres. They are very spaced out. There's a lot of space in between them. They move rapidly and randomly. So what that means is that these little gas particles, like, let's pay attention to this one right here in particular. They move. They are moving all the time, everywhere. When it hits this wall, what it's going to do is bounce off. And it might back to the wall. And then it might bounce over here and hit this one. And then it might bounce down and hit the bottom of the container. But the whole point of this is that our gas particles are going wherever they want to. They're bouncing all over the place. They're just in non-stop motion. Now, they have to be in constant motion, because if they slow down, they'll no longer be a gas, they'll become a liquid. There's no attraction between each other, so it's not like they make a beeline for another particle. They just go wherever, and if something happens to be in their way, then they hit it, they bounce, and they keep going. Now, unlike what you and I know of everyday life, these collisions are elastic. What that means is this. If it was a bouncy ball that was dropped down to the imaginary floor right here, then elastic means that bouncy ball would bounce down and it'd bounce right back up to the same height that it came from, and then it would bounce down again and right back up to the same height that it came from, and it would just keep going up and down to the same height indefinitely. Well, that's not how it works in real life. Real life is not elastic. So if you drop a bouncy ball, whether it's a basketball, a tennis ball, or whatever, in real life it bounces, and then the next time it bounces a little less, and a little less, and a little less, till it's just still. And even if it did it in the same place, it would bounce up and down, and then maybe this high, and the next time maybe this high, and each time it would bounce a little less till it stops. That is inelastic. So gas particles have to move elastically. They have to just keep going and going and going and going like the Energizer Bunny. Okay, and then because they're so spread out, you can compress them, you can smush them against each other. So pause it if necessary, make sure that you have all of this written down, and then you can move on when you're ready. Pressure. This is mostly vocabulary words for you. You have gas pressure, vacuum, atmospheric pressure, and barometer. You need to know the definitions of all four of these words. The biggest and most important thing with pressure is that it's caused by collisions, which means more collisions, the more things collide. More collide equals more pressure. So anything that you could do to increase collisions will increase the pressure in a gas. Now with atmospheric pressure, the main thing that my students will mess up here is this bullet right here, the second bullet underneath of the atmospheric pressure part. I guess it's the first one underneath it technically. But what my students will mess up is this. If we have a mountain and like let's say a small hill or a flatter area, and we have a person standing up here versus a person down lower here. Oops, I don't know what just happened there. We have a person down here. This person up here, if we pretend like the upper layer of our atmosphere is right up here, I just drew the lines. This person on top of the hill has this much air pushing down on them, whereas the person who's lower has a lot more air pushing down on them because there's a lot more atmosphere up above them. The higher you are in altitude, it's like the more shallow you are in the atmosphere. Think of it like a swimming pool. So there's not as much pushing down on you, there's not as much pressure. And the deeper you are into the atmosphere, the lower you are towards sea level, the more atmosphere that you have pushing down on you. Now, students nod their heads like, yes, I get this, but then the first thing that they do is they flip it around. And they want to make it to where if you go up in altitude, you go up in pressure, and that's wrong. That's backwards. And then you can read your definition of a barometer and how it works. This should be a capital H. I missed some of my caps here. So that is mercury. There's liquid mercury that goes down inside this tube, and then it causes it to rise. So pause if necessary. Make sure that you have this, and then move on when ready. Okay, pressure units. Since we're talking about pressure, and we're going to be using these in the latter part of the module when we do our math, you need to be familiar with these right here. And actually, your reference table has one more. It has 760 decimal torr, T-O-R-R. All 4 of these are on your reference table. You are not required to memorize these. They're on page 1 of that table. This does have a decimal there on your reference table, so you need to know that these are there. They are all at standard, they're all standard pressures. Basically what that means is that they're all the amount of pressure that is required to be at basically sea level at 25 degrees Celsius. That should be a capital C too. So they're not exactly, they are all equal to each other, but their numbers are very different except for the torr and the millimeters of mercury. So we'll use these quite a few times. Just know where to find them. All right. Now, we need to talk about kinetic energy and temperature. Remember, this means motion. So basically, the bottom line idea here is that when you heat up a substance, you're adding energy to it. And so it goes faster and faster. So if we have a container here and we could put one tiny gas particle inside of it, we'll put a lid back on top so it can't escape. If we could heat up this particle, you know, if we use my little cursor as the particle, at first it would be going slowly. It would be bouncing all over the container. And then as it gets hotter, it starts to move faster. And, you know, the more energy you put in there, the faster and the faster it would go till it's just going all over the place. Okay? So, you know, your relationship is right here. If you increase the motion, you increase the temperature. If you decrease the motion or the kinetic energy, then you decrease the temperature. If this was moving very rapidly and randomly and you set it outside, then it would start to slow down because you take away the energy. Like this morning was very cold, it would slow it down. Make sure that you get all this before you move on. Now, temperature itself, if you take a thermometer and measure something, is actually a measure of the average kinetic energy. So like if you take the temperature of a room, you're getting an average of the area around the thermometer, because if you have devices on in the room or people in the room, windows, things like that, there's going to be slight differences. So the average is what's used. The thing that I want you to realize here is what absolute zero is. Okay, absolute zero is 0 Kelvin. It is the temperature where particles have 0 kinetic energy. So Kelvin is preferred by scientists because it has a bottom point, like there's a lower end to it. This is as low as it can go with 0. There's no negative temperatures, and there's a true meaning to the temperature, which we'll see on the next slide. In Celsius, it's right here, and I believe in Fahrenheit, it's like minus 460 degrees Fahrenheit, if I can recall the last time I looked it up, which is really, really cold. Now, as soon as you have this, make sure that the video continues, and we'll go to the relationship between temperature and energy with Kelvin. The Kelvin scale is perfect because it reflects the differences, and I gave you an example down here. Kelvin temperature is proportional to the amount of energy. So if you go from 200 Kelvin to 100 Kelvin, you now have half the energy that you did before. 200 has twice as much energy as 100. 100 has half as much energy as the 200. If we had a third object at 50 Kelvin, 50 has half of what 100 does. It's got a fourth of what 200 does, or 200 is 4 times as much as 50. You can't do that with any other temperature scale. A couple of other things to point out to you about Kelvin. First of all, you notice there's no degree symbol. It is not 50 degrees Kelvin, like that's a big fat no. It is just simply 50 Kelvin. It's a capital K, not a lowercase. And on your reference table, page 3, you have a formula. You don't need to know this from your notes, but this is on your reference table. You have a formula to convert Celsius to Kelvin, and we will be using this. You just simply add 273. So 0 degrees Celsius would be 273 Kelvin. 5 degrees Celsius would be 278 Kelvin. It's really simple. Make sure that you have this, and you can move on to the next slide. There's no more info. It's down to practice time. So a lot of your practice for this is going to be conceptual. It's about vocab and concepts, like do you understand when temperature would go up in relation to energy? You understand where pressure would go down in relation to atmosphere or altitude. So if you need help, you know how to find me during office hours. And basically, we'll have more lessons like this in the near future, and we'll switch over to math.